All right, I guess we're going to try another one. By the way, I miss you guys. I miss being together and learning some mathematics and just interacting with you guys. I hope these videos are helpful and kind of just bring a little bit of what normal life should be like for us, for what you signed up for, not clearly what has happened. But we're going to look at a problem where we're going to use a combination of integration and differentiation in a non-calculator based setting, using a little bit of geometry as well as, it turns out they're going to actually use a little bit of chain rule and sneak that in on a problem. So we're going to be looking at the 2014 problem number 3. And so here we go, and let's see how this goes. So what we have right up here is this function, and notice this is function f. And as they describe function f down here, they actually say something that's very, very important right here, that it consists of 3 line segments. So you don't have to make any assumption about the fact that the rate of change of each individual segments is a constant. They're telling you that it definitively is. So you'll notice right here they're saying, so the graph that we have is f, but g is being defined as the integral, which of course tells you the value for the integral is the combined area between -3 and any value x. So if they ask for g of 3, what they're asking for is for g of 3 to be precisely the integral from -3 to that x value, which they told me was 3 of f of t dt. So I want to just look up here and figure out what that area is. And what you notice right away as I proceed from -3 up here to +3, we have an accumulation of area that's going to happen in here. And depending on how you want to look at it, I like to look at this as a simple triangle whose base is 5 units long from here to here, from -3 to 2. So it is 5 units long by 1, 2, 3, 4 units tall. And of course, the area of a triangle is just base times height divided by 2. Now notice you can't use a calculator, but that's obviously fairly simple calculation. And then over here, we have a little triangle, but they did something for us that is actually a little bit helpful. Because of the rate of change of this thing, you can see that it goes over 1, 2, and down 4. So it has a constant slope of -2. So if it went over 1 and went down 2, then that means this area of this little triangle here is 1. However, we want to keep in mind that that area is actually negative. And so we got our answer of 9 for part A of that particular question. Now, one thing that's nice is we've actually talked before about how sometimes open versus closed can be a little bit tricky when you're talking about analyzing curves. But in this particular case, they're letting us off the hook and saying it's an open interval anyway. So they're asking, where is G? And you have to be very, very careful because they're playing back and forth between describing F and describing G. So remember, G is the area under the curve. So they're asking, when is the area under the curve increasing and concave down? So we're going to have to break that down. So first off, to know when G is increasing, I want G, not F, excuse me. I want G prime to be positive, and to be concave down, I want G double prime to be negative. But if we look above, what you can see is what is G prime, but according to fundamental theorem of calculus part 2, that the derivative of an integral is that original function evaluated at the variable. So we know that G prime of x is in fact f of x. And therefore G double prime of x is in fact f prime of x. So when we look at when we want G to be increasing, I want to know when is F positive. Well, F is positive on the interval from -5 to +2. Well, I have to be a little bit careful because it actually would be positive on -5 to -3. Also positive from -3 to 2. okay, because of course it wasn't actually positive at -3. And then the question is, when is f prime positive? Well, in other words, when is the slope, oh, excuse me, when is it negative? Well, that would, of course, happen on this chunk right here from -5 to -3, and then from 0 to 4. So from -5 to -3, unioned from, let's see, 0 to 4. So it appears to me that according to that, so both increasing and concave down on -5. I guess, you know, the AP test doesn't usually like things to be written in interval notation, so I'm going to go ahead and write them in an inequality version. So this is the region where it was both increasing and concave down, but then there's also that interval from 0 to 2. And so that kind of sums up that particular part of the question. Now, what's interesting to me is they kind of seem to almost abandon this whole process right here, and they go to just almost like a basic old chain rule and quotient rule problem. So h is some new function that is a ratio of g of x to f of x. So what we're going to be doing is we're going to be looking at h prime of x. One moment, please.
Zoom bombing, I'm Zoom bombing.
Yes, we got a Zoom bomber, ladies and gentlemen. Mr. Jones is popping in on us. So let me stop share for a second so Mr. Jones can say hi. Howdy. We're social distancing, kind of. All right, so I had a little visit with Mr. Jones there. So anyway, we've got a little quotient rule. So of course, what we're going to do is we're going to go ahead and enjoy our little low D high. And we haven't done a low D high for a while. So here's my low D high minus high D low, but the derivative of 5x is just 5. That was pretty nice. Over the square of what's below. And notice I had to square not just the 5, but the x and the 5 and the x. That's 25x squared. And they're wanting to say, what is h prime of 3? So we get to now plug in 3 for all these x's. So if the first thing is, of course, we got 5 times 3. We've got 15 right there. We're going to have g prime of 3. We're going to have g of 3. We're going to have this 5 right there. And we've got 25 times 9, which, of course, is going to be 225. Now, interestingly enough, g prime, as we've established on one of the earlier problems, we said that g prime was f itself. So if they're saying what is g prime of 3, that's in fact saying what is f of 3. And so what is f of 3? Well, f of 3 over here was in fact 1, 2, 3. F of 3 was in fact -2. So this value is -2. And minus g of 3, let me be a little bit careful of that, but we actually found g of 3 earlier. G of 3 we found in part A to be the number 9. And so we've got 9 times 5. And so again, we've got a pretty simple little idea. We got -30 minus 45, excuse me, over 225, or -75 over 225. And honestly, on the test, if you actually stopped right there, they would not dock you at all. But that's actually a pretty nice set of numbers. That actually reduces all the way down to -1/3. And now our last little problem, this one, of course, was focused more on chain rule, using some of the information we had above. But now we're going to go, quotient rule. But now we're going to go ahead and look at a little bit of chain rule. So if we're going to find the slope or the rate of change of that line tangent to P, so they're going to look for what is P prime of -1. That's my question. So the first off is, what is P prime of X? Well, this is a perfect chain rule problem. So the derivative of this is the derivative of the outside function times the derivative of the inside function, which of course the derivative of x squared minus x would be 2x minus 1. And so if we're looking for P prime of -1, we're looking for f prime. If I plug in -1 here, I would get +1 minus -1, which is 2. And of course, if I plug in -1 right here, I get, I believe it is -3. And f prime of 2, as we mentioned earlier, comes from the slope of that value, which of course is -2 times -3 for a total answer of 6.
Don't bother, just put them up there. Put me up there.
All right.
This
Our visitor
is
back.
not for COVID. I'm allergic to math. Okay, I'm allergic to math, so I want this form
Awesome.
signed.
All right, everybody. Well, I hope that actually works for you, and I look forward to seeing you again, hopefully back here soon.